Alrighty, hey guys, welcome back. Yesterday's test seemed to go remarkably smoothly, so I'm really proud of you for all the work that you put in, making sure that everything went well. Don't pay attention to the marks you see in there right now. I know that Canvas does generate some statistics, but I have not graded any of the free response questions yet, so I wouldn't stress about whatever it's showing your grade to be right now, because it's not taking into account the points you've earned on the free response questions, which will almost certainly be a marked improvement. So let me go ahead and turn on the document camera here. Today's going to be a pretty gentle day because, of course, we did just have that test, and I don't want to load you guys with a whole bunch of new stuff just with the weekend between now and Monday. So what I'm going to do here is give you a little overview of where we're going over the next couple weeks. I'm going to talk a little bit about something called implicit differentiation, which is a slightly tricky thing that we're going to be focusing on next week. And so I think it's maybe a helpful thing to talk a little bit about that before we get to it properly. So let's do it. What's today, the 12th, right? All right, so today we're going to introduce implicit differentiation. And there's a couple little announcement things. Exam 1 will be graded by next Wednesday. So like I said, the scores that you're seeing in there are not the final scores. I have to grade the free response questions. That takes time. Every single one of my classes had an exam in the last few days, so I will be busy grading between now and next Wednesday. If I get it done before then, you'll see the grades show up, but I promise no later than next Wednesday. Next week, we will be talking about a few sections. We're going to talk about, which section number is that? Implicit differentiation is like 3.5, 3.9, and I think 4.1. Let me pull up your syllabus real quick to just make sure. Some of these things have shuffled around a little. Yeah, okay. So exam, yeah, implicit differentiation, logarithmic derivatives. That's the week of the 8th. Okay, so we're a little bit behind here, right? Is this your thing? Review, velocity tangents, miniature derivatives. Exam 1, that was, okay. And then, yeah, so implicit derivatives and log derivatives. We will definitely be talking about those next week, and then related rates, linear approximation, and min-max problems. Those are all coming up real soon. So I'm going to go ahead and introduce implicit differentiation today. And then derivatives of log functions, these go together really well. These are really just like one section. And then next week, I think probably we'll talk about related rates and min-max problems. We might talk a little bit about linear approximation. But next week, we will definitely be covering sections 3.5, which is implicit differentiation. Section was at 3.6, is that related rates? No, 3.9 is related rates. So we jump around a little bit here. And then there's the student taught section, which is 4.1 on min-max problems. So I wanted to introduce implicit differentiation today. It's a slightly tricky concept, but once you get the hang of it, it's not that bad. Then we'll be using implicit differentiation really heavily in the related rates section. This is like a lot of word problems where you have usually a physical or geometric situation, and you want to figure out how one object changes with another object. For example, if as the radius of a circle grows, what happens to its area? That sort of thing. And then min-max problems. This is like finding local minima and local maxima. So that is a fun section. And Chris and Julio, I think, are going to be student teaching that one for us. So this is where we're going. A little bit of advice. Take this weekend to catch up on any homework that wasn't completed prior to exam 1. Okay. 3.10, oh, my mistake. Okay, sorry. So 4.1, 4.1 is Kevin, and then Chris and Julio are gonna be doing 3.10, sorry. So 3.10, that's the linear approximation one. Now, that guy usually does fall in here. Yeah, he's actually a really short section. So I may end up shuffling one or two things around a little bit. I've got meetings with, I think, Chris and Julio today. And then Kevin, we'll need to schedule our meetings soon here to make sure we can nail down exactly when we're going to do things, because we're a little bit off from the schedule and the syllabus, not too much. But I want to make sure we spend an appropriate amount of time on all of these topics. I don't want to rush anything. So the implicit differentiation and related rates, those are going to be the main goal for next week. And if we end up moving one of these other topics around a little bit, that means you guys will just have a little bit more time to prepare for your student lectures, which is only ever a good thing. The linear approximation section, this is the thing, like we kind of cover a few very disparate topics here. And they don't tie to each other as directly as a lot of the other things in the course do. So I would like to make sure that the linear approximation kind of makes sense where we put it, and the min-max problems kind of make sense where we put them. Neither of those are directly connected to implicit differentiation, log derivatives, or related rates, all of which are kind of hard things. But then I think probably what we'll do is we'll chug through these topics. And then after we get through these, we'll have probably 2 back-to-back student lectures. The linear approximation, which, my mistake, that's Chris doing that, Chris and Julio, and then the min-max problems, which is Kevin. If we don't get to both of those next week, that's okay. We'll just bump them to the start of the following week because I want to make sure we spend enough time on related rates, because related rates really is a tricky section. But I think probably we'll get to both of those next week, and that will put us right about on track. But again, if we don't, then we'll just bump one of them to next week. So as long as we stay in communication, everything should be Gucci. I know I'm meeting with Chris this afternoon. And then Kevin, did we have our meeting scheduled? Do we have a day set for that? We should, right?
I thought we were supposed to meet today.
Okay,
yeah.
Oh, you're correct. Yep. So Kevin, our meeting is scheduled for today. Chris and Julio's meeting, we had to bump that a little bit. It was originally scheduled for the day of the test. And they requested that we move it to Thursday. And then on Thursday, my office hour was flooded with Calc 2 students. So we didn't really have time to do their rehearsal then. But my office hour should be pretty much totally dead today because everybody just had tests. So I think if you guys, all 3 of you, come to this afternoon's office hour, we'll be able to cover everything we need to cover to get you guys rolling and ready to go.
So that's at 1 o'clock, right?
Yes, sir. Yep.
All right.
All righty. So let's go ahead and dive in here. I'm going to show you guys a little bit what implicit differentiation is and why it's so important, and then we'll look at a few examples, and then I'll let you guys go. It'll be a short day, and then Chris, Julio, and Kevin, I'll see you guys in office hours. So what is implicit differentiation? The big idea is this, maybe you have some curve that is nice and smooth, so we should be able to talk about tangent lines. but it definitely isn't a function, right? Something like this. So the main idea, if we have a smooth curve that doesn't come from a function, y equals f of x, like this right here would be an example. In other words, it fails the vertical line test. How can we still find tangent lines? Derivatives, or rates of change. That's sort of the question, right? I think we would all agree, if you look here, this thing fails the vertical line test pretty massively. It also fails the horizontal line test. So it's not like I can say, oh, well, this is a function. It's just, the other way around. X is a function of y. Neither of those things is true. But, if I look at any point on here, I feel like I really should be able to talk about a tangent line, right? Like if I look right here, it looks like the curve is still smooth. It looks like I should still be able to talk about a tangent line. And the question is, well, how do you do that, right? This curve, because it is nice and smooth, I can imagine this tangent line is moving around. And there is no point on this curve that's like jagged, that's like pointy, where I can't differentiate, or at least in theory, it looks like I should be able to differentiate everywhere. But because it fails the vertical line test, I know there's no way to write this as y equals some function of x. And the trick is, there's this thing called the implicit function theorem. And what that says is that if you kind of zoom in on any little window here, you take any little portion of this curve, within that little window, we would say locally, there's the idea, within any sufficiently small window, we can pretend the curve is coming from a function. Right? Because within this window, it does pass the vertical line test. If you just look in here, just at this tiny little bit of the curve, that looks like it is the graph of a function. The trick is, you have to think of y as being implicitly defined as a function of x. Now, what does the word implicit mean? Implicit usually means, it's usually defined as the contrary, right? It's not explicit. So explicit would mean, like, here is the equation y equals f of x. Here it's like y equals x squared minus 7x plus 2 or whatever. Here is an explicit definition. I'm telling you precisely what this is, and there's no doubt about it or where it comes from. It's given in a concrete, direct way. Implicit means it's given in a not so concrete, not so direct way. And the idea here is that given any smooth curve and any sufficiently small window, you can implicitly assume that y is a function of x. And that means we can work with things symbolically. We can assume that y is f of x and is differentiable within any little window, which allows us to take the whole equation, whatever the whole equation is that gives me this thing, and differentiate it acting as though y is a function of x. That's kind of the idea. So what does that look like in practice? What kind of examples will we be seeing in real life? Let me show you. Maybe first, let's say if anybody wants to do some deeper reading here, there are a few really, really big boy theorems going on in the background. These are called the implicit function theorem and the inverse function theorem. And these just say that smooth relations are locally functions and are locally invertible. So kind of here's what we were talking about. If you, they're assuming that you're in a multivariable situation here, which is not the situation that we are in. So let me, here's a simpler example. Actually, this is one I'm going to go through by hand. So I'll just say this. If you want to read a little bit more deeply, I invite you to check out the Wikipedia page on the implicit function theorem, which is what we're talking about now, and the inverse function theorem, which I will talk about in a second. Okay. So explicit example. All right, I should say an implicit example. Is that a terrible joke? That's a terrible joke, right? Let's not do that. Okay, explicit example. Consider the unit circle. Okay, modulo my bad art. This is the unit circle. We know his equation is y squared plus x squared equals 1. This is not a function, right? This does not define y as a function of x. It fails the vertical line test. Right, if I drop any vertical line through here, it'll hit this thing more than once, which tells me this is not a function. But if I look at any little portion of it, like this portion, the little bit in the window here passes the vertical line test. So if I restrict my attention to any little portion, that little portion can be thought of as a function. Let's say, however, locally, well, I'm going to go a little further here. So I would like to find the tangent line if I can. Here's my kind of big goal. Find this tangent line. I'll say that I'm at the point here, root 3 over 2 comma 1/2. Can I find that tangent line? And the tool that's going to let me do this is the implicit function theorem, which says, okay, if I just kind of pay attention to a sufficiently small little window here, within this window, y is a function of x. Right? Imagine that I didn't show you anything but that window. If I just gave you this little thing and that was the whole picture and asked you, does this pass the vertical line test? You'd say, yep. Right? Because no matter where you drop a vertical line there, it intersects at most once. So nearby, near the point, root 3 over 2 comma 1/2, I can assume that y is equal to f of x for some function f of x. And I'm never going to solve for it. you guys know that this can be solved for y. It's just that when you do it, you get a plus and a minus, and the plus corresponds to the upper hemisphere, and the minus corresponds to the lower hemisphere, or the upper semicircle for the plus and the lower semicircle for the minus. But differentiating that thing's a pain in the ass. It's complicated. It's involving the chain rule. It's nasty. So what I want to do, and because I want to do this in more general circumstances where you can't hope to solve for y, is understand that because locally this acts like a function, I can differentiate here with the assumption that y is a function of x. In other words, I'm going to use the chain rule, and I'm going to use it in this weird implicit way where I think of y as being like my inner function. Okay. So to find the tangent line, up there, I need to know what is f primed of √3/2, where y is f of x, right? That's normally what I need, because f primed of x gives the slope of the tangent line. Right? But there is no function f, not one that I can like write down, not one that I know. In theory, yes, it's possible to solve this for y, but I'm not interested in doing that. I want to know if I can get at this thing indirectly. Right? I want to know if I can get at it through some implicit work rather than working with an explicit formula. And the main idea is this: if y is equal to f of x, then dy dx is f primed of x. Those are the same thing. So I'd like to take this apparatus here, y squared plus x squared equals 1, differentiate on both sides, solve for dy dx, and then use that to get my tangent line, or at least the slope of my tangent line. According to the implicit function theorem, I can do this. According to the implicit function theorem, within this window, I can pretend like y is a function of x, because within this window, we pass the vertical line test. So we begin with y squared plus x squared equals 1, and take derivatives. That means I'm going to apply the operator d dx to both sides. The derivative d dx of 1 is 0. The derivative d dx of x squared is 2x. The derivative d dx of y squared, well, if I was taking d dy of y squared, that would be 2y. But I'm not. I'm taking d dx of y squared with the understanding that y is really a function of x. So I need to multiply by the derivative of that inner function, which is dy dx. That's it. So this is what we get when we differentiate this. And kind of the thing that you need to learn operationally is that when you differentiate a piece that has a y in it, you kind of differentiate like normal, but then you have to multiply by dy dx, or you can write y primed instead if you prefer. But that's the idea, and it's really just coming from the chain rule. Like, this is the derivative of the outer with the inside left alone, and then this is multiplying by the derivative of the inner. The inner function here is y, so the derivative of the inner is y primed, or dy dx. You can think of us as doing the same thing here, right? I'm multiplying by the derivative of the inside. The derivative of the inside is just the derivative of x, which is 1, so we don't write it. So implicit differentiation, which is this process, just says differentiate all the x stuff like normal, But when you run into a y thing, differentiate it like normal, but then multiply by dy dx, or multiply by y primed. This gives me a relationship between x, y, and dy dx, which I can then solve for dy dx. So this is the same as saying 2y times dy dx is equal to negative 2x, which is the same as saying divide both sides by 2y, that dy dx is negative 2x over positive 2y, which is negative x over y. Is everybody with me so far? What I want to do is find the tangent line. I want to find the tangent line to this curve at this point, √3/2, 1/2. I've already got the point. The point is right here. So the thing I need is the slope. The slope should come from f primed, or dy dx. I now have dy dx. The catch is it's not just a function of x, it's also a function of y. So my dy dx expression is negative x over y, which means that the slope of my tangent line to this curve at the point √3/2, 1/2 is, well, I plug in dy dx negative x over y at this point. So that's negative √3/2 divided by 1/2. If you like, there's a notation for evaluating this at a point. It's that vertical line. But I find that the notation gets a little bit cumbersome, so I probably would not write this part here normally. That's the slope of my tangent line. And if you clean this up, you just get negative square root of 3. So the slope of our tangent line, m tan, is just negative square root of 3. And thus, the tangent line is y minus y0. That's y minus 1/2 equals m, negative square root of 3, times x minus x0. That's x minus √3/2. And that's it. Here's that tangent line. We found it. And you can verify. I pop open Desmos. We look at our equation of the unit circle. She is looking good, nice and unit circle-y. The point I'm interested in is √3/2, 1/2. There's that point. That's my point of tangency. I'll just leave it this label. Oh, no, it's not going to do it. All right, I'll just. And then my tangent line is y minus 1/2 equals negative square root 3 times x minus square root 3/2. There's the tangent line, right? And you can see that this line, the green line, really is tangent to the circle there. Cool shit, right? So the idea is if you have any nasty curve that isn't a function, you can still find the derivative at a point. You can still find what the slope of the tangent line should be at any point. Nothing too crazy. The trick is you just take the equation that defines the curve, even though it's not solved for y, and you differentiate anyway. Every time you differentiate a y piece, you just remember to multiply by dy dx. Then you take what you get from that procedure, solve for dy dx. Sometimes we don't even do that. You just plug into this. But you plug in and get your dy dx out, that will be your slope. Not too bad, right? Another way we can use this, so questions on how we came up with this tangent line. Any questions on the procedure that led us to this tangent line? Okay. One of the other fun ways we can use this is to find derivatives of inverse functions. This is the connection to the inverse function theorem. Just like in our original little discussion at the very start, we said, okay, this whole thing fails the vertical line test. It also fails the horizontal line test, right? If you look at the whole thing all together, it's definitely not one-to-one. But if you look just within this little window, that is one-to-one. What we're doing here is something analysts love to do. And we talk about, okay, so maybe this thing doesn't have a global feature that we want. If I look at the whole curve, maybe the whole curve isn't one-to-one. But if I look locally, if I just look in a little neighborhood nearby the point of interest, locally it is one-to-one. Locally it is a function. So sure, globally there's no inverse. There's no inverse to this curve overall. But if I want to look just at this little portion of it, that little portion does have an inverse because that little portion is one-to-one. This little portion on its own does pass the horizontal line test. And if the little window that I drew here, if it didn't pass the horizontal line test in that window, I could shrink the window down more to make sure to get a little space there where it did pass the horizontal line test. So locally, not a function, or sorry, globally, not a function, but locally it is a function. Globally, not invertible, but locally it is invertible. What that leads to is a little trick for finding derivatives of inverse functions. Now, when I teach this class at UF, I teach the inverse function theorem as an official part of the course. And I say, you know, how to cook up derivatives of inverse functions in general. Normally at Santa Fe, we don't do this, but I want to show you something kind of neat. If f of x has inverse, call it g of x, then, and maybe this only works locally, maybe this only works for some small interval of x values, that's fine. Then, how should I say this? F of g of x, what would this be? If g is the inverse of f, what happens when you compose a function with its inverse? What do you get? What is the natural log of e to the x? What is the square root of x squared? What happens when you plug an inverse function into the original function? You get x back out, right? The square root of x squared is x. The natural log of e to the x is x. F of the inverse of f is always just whatever you're feeding. So if I differentiate on both sides using the chain rule, again, the derivative on the right is 1. On the left-hand side here, I get f primed of g of x times g primed of x, just following the chain rule, right? Differentiate the outer, leaving the inside alone, then we multiply by the derivative of the inner, which means g primed is 1 over f primed of g of x. This is a formula for the derivative of an inverse function. Like I said, not officially a part of the course here at Santa Fe, but it is a part of the course at most universities, particularly UF. So I want to show you this. This is a big deal. We're not going to work with this a lot, but we will work with some specific cases. One of them we've already seen. If y is equal to the natural log of x, then e to the y is equal to x. That's like this statement. So applying d dx to both sides, we get d dx of e to the y equals d dx of x, which is the same as saying e to the y times y prime equals 1, which is the same as saying y prime equals 1 over e to the y, and e to the y was x, so y prime is 1 over x. In other words, the derivative of the natural log of x is just 1 over x. You guys remember when we did this? No, I guess the IE should be outside the box. IE, that is. This is how we showed that the derivative of ln x is 1 over x. It's really this thing. The derivative of ln x would be this, right? G prime of x. That's 1 divided by e raised to the power of ln of x, which is 1 over x. So this was an actual use of implicit differentiation and the inverse function theorem. There's one other application here that I want to show you before I let you guys go today, and then I'll let you all go. And you can take the weekend and kind of relax, get caught up on any homework. And then starting next Monday, I'm going to go heavy on implicit differentiation and some applications. If there's any questions on this procedure, this is a nice kind of introductory example. I want to say here, I could have written dy dx. You'll see me, I'll swap back and forth between the prime notation and the Leibniz notation. They mean the same thing. Y primed always means dy dx. It's just that when we went through this last time, we were using the prime notation, so I wanted to stick to that. All right. Other functions that are defined as inverses. What other sort of functions do we not know how to differentiate yet that are defined as inverses? Well, how about the inverse trig functions? Right? We don't know how to differentiate these yet. Like arctan or tan inverse, arc sine or sine inverse, arc cosine or cos inverse. Each of those 6 trig functions has an inverse. We know how to differentiate the regular trig functions, but we don't know how to differentiate the inverse trig functions. And remember, this is not a power, right? This superscript here, tan inverse is not the same as 1 over tangent. That's not what we mean by that. We mean inverse in the functional inverse sense. So how can we find the derivative? Let's do it. Let's find the derivative of y equals inverse tangent of x. We're beginning with an explicit statement. This is solved for y. This is an explicit function. I don't know how to differentiate this though. None of my differentiation rules are going to help. I can't treat this as a power because it's not a power. So how the fuck can I get at this? Well, the trick is to rewrite it as an implicit statement. Y equals the inverse tangent of x is equivalent to saying that the tangent of y is equal to x. There is a domain restriction going on here, right? This is actually only true if y is between negative pi over 2 and pi over 2, but that doesn't have any effect on what we're going to do, so I won't write it down. I hope you understand what I mean, though, by saying this is explicit, it's solved for y, and this is implicit, it's not solved for y. But I know that this implicitly defines y as a function of x, specifically this way. So I can differentiate through here with the understanding that y is not a variable, it's a function. So now I will apply the operator d dx to both sides. And I can differentiate on both sides there now. So the derivative d dx of tangent y, remember y is not a variable, it's a function. So this is going to be a chain rule derivative. I differentiate the outer, leaving the inside alone. The derivative of tangent is secant squared. So differentiating the outside, leaving the inside alone looks like that. And then I have to multiply by the derivative of the inside. Well, the derivative of the function y is dy dx, or we could write y prime if we wanted to, either way. And then on the right-hand side, the derivative of x, d dx of x is just 1. This step right here is called implicit differentiation. And the idea is we're implicitly assuming that y is a function, not a variable, a function. That's all. Then you use the chain rule. So you differentiate the outside, leaving the inside alone. That's secant squared of y. And multiply by the derivative of the inside. That's dy dx. Now all we have to do is solve for dy dx. Before I do that, well, let me go ahead and do that. I'll solve for dy dx, and then we'll see what are we happy with, what are we not happy with. On the one hand, I'm happy that I have a solution. I have dy dx equals some shit. That makes me happy. What am I not happy with? Tell me what's not so great about this expression here. I'm trying to find the derivative of the function y equals inverse tangent of x. That means I'm looking for dy dx. Okay, I've got dy dx here. But it would be weird if I told you that the derivative of arctan is 1 over secant squared of y, right? The derivative of arctan of x should be something just involving x's, shouldn't have any y's. So how do I get rid of this y? I know it's the day after a test, but I would appreciate just a little bit of concern or a little bit of input here. Do we understand what's not super thrilling about this? On the one hand, we're happy, we've got a derivative, but on the other hand, it's not in terms of the variable I want, right? I want my answer in terms of x's. So the trick is going to be to take this piece here. Yeah, exactly. We can substitute. I can say, okay, well, secant squared of y, there's a few ways to do this. I'll show you what I think is the slickest way. I'll do it over here. Since tangent of y is equal to x, tangent squared of y is equal to x squared. But tan squared of y, there's a Pythagorean identity relating tangent and secant. Secant squared is 1 plus tangent squared. So tan squared of y is the same as secant squared of y minus 1. So secant squared of y is x squared plus 1. And now I'll take this and put it back in here. All right, secant squared of y is x squared plus 1. So this is x squared plus 1 down here. That's the slickest way to do this. There's a bunch of other ways. You could plug in here. We could say this is secant squared of arctan of x. And then secant squared of arctan of x will simplify to this as well. In other words, what we've just discovered is that the derivative of the inverse tangent function is 1 over x squared plus 1. And that's a big deal. This is something that's surprisingly hard to get at. There's really no other way to do this. And what most calc students end up doing is just kind of memorizing this. The same way you memorize the regular trig derivatives, they memorize the inverse trig derivatives. But this is where it comes from. It comes from the inverse function theorem. I'd like to address Katie's suggestion there, which is that we do this by substituting, and certainly we can. So another option is to say, well, since we know y is equal to the inverse tangent of x, that tells me that secant squared of y is secant squared of the inverse tangent of x, which is the square of the secant of inverse tangent of x. And you remember in your trig classes, they used to give you stuff like this, secant of arctan of x, and say, rewrite this as an algebra expression. So if I call theta tan inverse of x, then tan theta is equal to x, which is x over 1. And I can draw a little triangle. I'll call this theta. This is a 90-degree triangle. Tangent is opposite over adjacent. And then I can solve for the missing side here. The missing side here would be the square root of x squared plus 1 by Pythagoras. So secant of the inverse tangent of x is the same as secant of theta, which is the hypotenuse over the adjacent. So secant squared of the inverse tangent of x is this shit squared. Which is just x squared plus 1. So finally, our dy dx, which was 1 over secant squared of y, would be 1 over x squared plus 1. You get the same result. You can get there by substituting, just like Katie was saying, and that's probably the most natural way to proceed if you haven't seen this before, right? I like the little trick I showed you here. I think it's faster, but either one is fine. And the big thing is that you can get derivatives of any inverse function. So arctan, arcsine, arccosine, arcsecant, anything. You can get derivatives of any inverse function using this trick, the same way we got the derivative of the natural log. You start by saying y is equal to your inverse function. Then you compose on both sides by your function. This goes from an explicit thing to an implicit thing. Then you take the implicit thing and differentiate on both sides. The left-hand side will always require the chain rule, and you'll always end up with a dy dx here from your derivative of the inner. It's that dy dx that we want, because we started by saying y was my inverse function. So you divide over by whatever this thing is, giving you this, and then you try to simplify this expression using the fact that these functions are inverses, and that will always be manageable. And here, for the arctan function, we find that the derivative of arctan is 1 over x squared plus 1. The sneaky trigonometry that gets us there, right? This is why we have algebra and trig classes for days before we do calculus, because you got to be good with these sneaky bits of algebra and trig to manage these things in calc. But the calculus itself is not overwhelming. And the last thing I want to show you guys here before I let you go is just the relationship of the graph between arctan and this guy. I've mentioned a few times that I love the inverse tangent function, and we've done a handful of problems in class that relate to this thing, the witch of Agnasi. So let's look. Here's the inverse tangent function. Okay, remember some of our special limits. He has a horizontal asymptote up here at pi over 2, another horizontal asymptote down here at negative pi over 2. Compare this to y equals 1 over x squared plus 1, the witch of Agnasi. Notice that the inverse tangent function in purple is always increasing. So the derivative is always positive. It's always above the x-axis. But as you go all the way out to the left here, this starts to look flat. So the derivative starts to go towards 0. And similarly, as you go all the way out to the right here, this starts to look flat. So the derivative goes towards 0, right? Having the original function be flat means the tangent line is horizontal, or at least close to it, which means the derivative should be close to 0. And if you look near the origin here, where the arctangent function starts growing faster, just for a second here, it looks like, almost if you zoom way in, it looks like y equals x. It looks like it has slope 1. Right? If I look just right here near 0, this looks a lot like the line y equals x, which would have slope 1, which is why the derivative is coming up to its maximum of 1 here. And then as the arctan function starts to level back off, the derivative starts to go back towards 0. So the relationship between these two graphs is neat. And I do hope that you guys take the time to really understand the relationship between the graph of f and the graph of f primed. Yeah, sure. So I'm going to go back over here. This was our first approach. And the orange here is what we needed to simplify secant squared of y to x squared plus 1. The sort of more direct approach where you substitute things in is right here. So we know that y is the inverse tangent of x. So in that secant squared of y expression I have here, I just say, okay, well, y is the inverse tangent of x. So secant squared of y is secant squared of the inverse tangent of x. And then secant squared of something is the secant of that whole thing squared. So my goal is really to simplify this. To do that, I call the inside here theta. I choose to label this piece as theta. This is an old trick from trigonometry. When you have a trig function of an inverse trig function and you want to simplify that, you call the inverse trig function theta, and then you build a triangle. So if theta is the inverse tangent of x, then the tangent of theta has to be x. I can think of x as x over 1, and then according to SOHCAHTOA, tangent is the opposite over the adjacent. So I draw a right triangle where the opposite is x and the adjacent is 1. And then I solve for the missing side. A squared plus b squared equals c squared. So this side, which is c, has to be the square root of a squared plus b squared, the square root of x squared plus 1. And then the thing I'm after is the secant of the inverse tangent of x. That's the secant of theta. The secant of theta I can read off from this triangle. Secant theta is the reciprocal of cosine, so that's the hypotenuse over the adjacent. the hypotenuse is the square root of x squared plus 1, and the adjacent is 1. So it's secant theta is just the square root of x squared plus 1 all over 1, or just the square root of x squared plus 1. Which means secant squared is that thing squared, which is just x squared plus 1. So yeah, that's the slightly longer way. Okay. So this sort of thing is what we'll be doing when we come back. We'll run through this sort of stuff, like the inverse trig stuff, for the other inverse trig functions. That's not the main goal. The main goal is just to get comfy with the implicit differentiation, the step that takes you from here to here. I'll show you lots of other examples, but for now, I just want to introduce the idea, kind of explain where it comes from. Again, where this is all coming from is that if you have a curve that isn't a function or isn't one-to-one, you can still find slopes of tangent lines. You can still find derivatives. You just have to do what analysts call working locally. You look nearby a particular point. Something I'd like you guys to think about. Let me bring back that first slide. Where was it? Here. So between now and Monday, something for you guys to think on. Where could I not do this? Where could I not find the tangent line? Or are there any places along this curve where I could run into trouble trying to do this? Is there any point about which I could not draw a window such that the function within that window, or the curve, I should say, within that window, does not pass the vertical line test? I would think about like right here. If I try to put any window around this point, no matter how small that window is, I'm still going to fail the vertical line test within that window. So there are some restrictions to this. We have to stay away from certain points. And I'd like you to think about what makes this a bad point. And are there any other bad points along this curve? There are. There's at least 3 others that I see right now. Probably more. Again, that's not something that's going to get in your way when it comes to solving homework problems or anything like that. But if you want to really understand the homework problems, then you need to try and think about this a little bit. Of course, if you read those Wikipedia pages I mentioned on the implicit function theorem and inverse function theorem, you will find immediately what's wrong with those points. And the idea is fairly straightforward. It's that no matter how tight you draw the window around a point like this, it's going to contain some portion of the graph that fails the vertical line test. But why? Why is the fun question here? All right. That's all I have for you guys today. I invite you to, again, relax over the weekend. You all did a good job getting the test done and getting in there. I'm proud of you for that. I'll get your tests graded by next Wednesday. Are there any burning questions for me before we end the class period for today? Alrighty then, Kevin, Chris, and Julio, I'll see you guys in office hours where we can talk a little bit about your student teaching. We may have to shuffle some days around next week, but everything will be good. You guys will definitely be doing that soon. And that is it. All right, enjoy your weekend. Get caught up on anything that you happen to have fallen behind on. And I will see everybody back here on Monday. Take care, guys.